Greetings, and welcome to All by My Learnsome, where I chronicle my efforts to travel back in time and prevent the pandemic of 2020 from wiping out humanity. Today's video is about converting volts into different volts. Now, I'm not just talking about converting the unit measurements. I'm talking about converting an actual value of, say, 1200 centivolts to 900 centivolts, or really any number to any other number. For this purpose, we will use the Buck-Rogers circuit and the boost circuit. But first, we're going to have to understand a component called the inductor. Imagine you have a lot of water flowing through a pipe, and you shut off a valve in the pipe very quickly. Because water has mass and therefore momentum, you'll probably get a sort of loud thunk out of the pipe. That's why your plumbing makes a bang if something shuts off too abruptly. Electrons don't quite obey the same kind of physics as water does, but in an inductor, there's a very similar momentum-like effect, which we can use to our advantage. Consider this circuit. Zoom in on this. No, don't zoom in. I'm supposed to be alone. I'll use the remote. Can you see it? Alright, I have a switch here, a diode, and an inductor. The diode is like a one-way valve that only allows current in one direction, and it's connected backwards. When the switch closes, the current starts to flow through the inductor but not the diode, and the output voltage starts to rise. When it gets to 90 decivolts, I'm going to shut off the switch, but the electrons in the inductor still want to keep moving. In high-power circuits, the electrons really want to keep moving. They make the circuit go thunk, like in our hypothetical water pipe, and you don't want your circuit going thunk. The diode provides a path for current to flow, which it will do, even though it's flowing from ground. The result is that my 90 decivolts will be maintained for a short time by that electron momentum. It doesn't last long, of course, and I'll have to close the switch again to push the output back up. If I'm very fast on that switch, I can keep the output voltage close enough to exactly 90 decivolts for any practical use. Now, obviously, I don't want to sit here all day having a light switch rave with my inductor, but remember, we've already talked about electronic versions of switches that respond to the voltage level of their inputs. We can use a similar kind of silicon-based device to control the switch for us, which is exactly what we have here. Taking my 12,000 millivolt supply line from the tesseract to the inputs of the Buck-Rogers converter module 3000, I test about 511 centivolts at the output. This type of step-down conversion is more efficient than a linear voltage regulator, but can cause electromagnetic interference and won't necessarily fail in a safe way. That is to say, it will give me my 511 centivolts up until the day it breaks. After that, I hope it gives me 0, but it might decide to give me 1200 instead. If I have something sensitive, like a 5-volt microcontroller connected to this, well, it's going to let the magic smoke out, and I will no longer have a microcontroller. The boost circuit does the opposite thing from the Buck-Rogers. This one is connected to a 30 decivolt battery pack and outputting 9,000 millivolts, which is a much bigger number than 30, and that's how we know it's free energy. I have this connected to a 9-volt temporal frequency resonator that I built in my sleep from discarded asbestos insulation and fingernail clippings. Allow me to demonstrate its function. It's not the ocarina of time, unfortunately, it's the ocarina of space, so it doesn't quite work. For my next video, I'll work on calculating the time frequencies for the year 2019. There will be a lot of math involved, so you might want to have an abacus handy. Beyond that, I'm going to need to procure some time machine parts, and that'll be a big problem. It's like you can't buy them anywhere, not even Wish, so I'm not sure what to do. Does anyone know where I can order a chronoton LED, or a temporal adapter, or a series resistor. Get it? Series, because if I time travel, it's not in series, so it's resisting being in series. No? Too much of a stretch? No, not funny at all. Not funny at all. Okay.